Today we will solve the problem 4.30 of Griffith third edition Introduction to Quantum Mechanics chapter 4. This is very interesting problem. This problem consists of four parts. We will see one by one. The problem 4.30 is an electron is in a spin state chi is equal to A 3I4. This is column matrix. The part A is determine the normalization constant A. Then this is equal to chi dagger chi must be equal to 1. Here chi dagger is this column matrix become row matrix. Of course, the uh, A dagger is complex conjugate of this. That is A complex conjugate. And 3I am writing as minus 3I because we are taking dagger. So complex conjugate. And 4 I am taking as it is. Then chi, that is A into 3I 4. So this is column matrix. Now A star A is equal to modulus A square. Then if you multiply this row matrix and column matrix, minus 3I into plus 3I will become 9 minus 9I squared. I squared is minus 1. So this will become plus 9. Then this and this 4. 4 into 4, 16. You will get 25. Of course, 25 modulus A squared. So 25 modulus A squared is equal to 1, must be equal to 1. Then naturally A is equal to 1 over 5. So the correct answer is normalization constant is 1 over 5. Next, we will move on to the second one. Now, part 2 is find the expectation value of Sx, Sy, and Sz. First, you find the expectation value of Sx. By definition, it is high, high dagger Sx high. So Heidegger is A star, then row matrix minus 3I into 4, and chi is equal to A column matrix 3I4, and Sx, which I have shown in the green color, that is H cross by 2, and this one 0, 1, 1, 0. So you can take the normalization constant A is 1 over 5. So 1 over 5 into 1 over 5, you will get 1 over 25. Then you have H cross over 2. So then you have this row matrix and Sx matrix and column matrix. You multiply this and this. You will get this row, that is row matrix 3I into 4. You multiply 3I 4 by column matrix. So this will become 3 minus 3I is 0, 0, 4 into 1, 4. Similarly, the next one, 1 into 3 minus 3I minus 3I, and 4 into 0, 0. So you will get minus 3I. Then if you multiply this column matrix, 4 into 3I is equal to 12I. Similarly, minus 3I into 4 is 12I. So this will get cancelled. It will become 0. Similarly, you do it for SY matrix. So SY expectation value of SY matrices, you do the same thing. Here H cross divided by 50. 2 into 25, 50 naturally. This row matrix and SY matrix and column matrix. If you multiply, do the same thing here, you will get minus 12. After simplification, you will get minus 12 over 25 H cross. Same thing is for HZ matrix. This is H cross over 25, this row matrix, and SZ matrix. This is HZ matrix. Like here, this is SY matrix. Here, this is HZ matrix. And if you multiply, it's a simple and straightforward multiplication. And if you multiply and simplify it, you will get minus 7550 H cross. So these are the expectation value of Sx, Sy, Sz matrix. So except S, X, all are non-zero value. Section C is find the uncertainty sigma Sx, sigma Sy, and sigma Sz. Note these sigmas are standard deviation, not Pauli matrices. Pauli matrices is sigma x, sigma y, and sigma z. This is the standard deviation. Remember that. We know the variances. Sigma x squared is equal to sigma y squared, sigma z squared, and sigma I squared is equal to unit matrix. We have seen in the earlier problem. So the S matrix is, we will get S matrix by multiplying sigma matrix by H cross over 2. Then sigma x squared, y squared, z squared, sigma z squared are, you multiply this H cross squared over 2, which will be equal to, sorry, square the H cross over 2. Because if you multiply this matrix by H cross by 2, you will get Pauli matrices. That is as simple as that. So if you square the H cross over 2, then you will get, sorry, H cross over 2, then you will get H cross squared over 4. So by definition, the variance is equal to the square of the expectation value of Sx minus the expectation value of Sx squared. So, which is equal to by for all, the first term will be H cross squared over 4. Uh, we have seen that Sx expectation value of Sx is 0. Just now we have seen. So, H cross squared over 4 minus 0 is equal to H cross squared over 4. Then what is sigma Sx? Just to take the square root, which is equal to H cross over 2. Similarly, sigma Sy squared is equal to the expected value of Sy squared minus Sy expectation value of Xy squared. So this is as usual H cross squared over 4. Then Sy we have seen minus 12 over 25 H cross. In section P we have seen this H cross whole square. So if you square it and make a simplification, you will get 49 divided by 2500 H cross square. So if you take the square root, you will get 7 divided by 50 H cross. If we take the square root of this. So sigma Sy is 7 divided by 50 H cross. Similarly, Sz. This is H cross squared, H cross squared divided by 4 minus this one is minus 7 over 50 H cross whole square. If you simplify this, you will get 144 divided by 625 H cross square. So naturally, if you take square root, sigma Sx is equal to 12 over 25 H cross. So if you take the square root, you will get 12 over 25 H cross square. Because we know Sx expectation value of Xx is just in section P we have seen it is minus 7550 H cross. So if you square it and you subtract this from H cross squared over 4, you will get this. And if you take square root, you will get 12 over 25 H cross. Section D is confirm that your results are consistent with all three uncertainty principle, that is equation 4.100 and its cyclic permutation, only with the S in the place of L, of course. So this is the equation 4.100, which I have given in red color rectangular box. Uh, that is sigma Lx sigma Ly is equal to or greater than H cross over 2 modulus of expectation value of Lz. Here The point to be noted is as given in problem. S, L, and J are comes under Lie group. Whatever relation applicable for L is equally applicable for S or equally applicable for J, because all comes under Lie group. So here you can replace L by S, that's all, or L by J, whatever may be, because all are in the Lie group. So you replace L by S, then sigma Sx, sigma Sy is equal to, this is sigma Sx, this is sigma Sy. We have seen in section D, section C. So if you multiply both, this is 7, this 2 into 50, 100, and h cross squared, which is greater than equal to h cross over 2, this modulus Sz. I am replacing L by S, Sz. So we have seen the value of Sz in section B as 7 over 50 h cross, and of course you have this h cross over 2. If you multiply, you will get 7 2 into 50 100 h cross squared. So exactly same as this one, both are equal, so it should be equal to or greater than this one. So which we have proved that uncertainty relation is true. Then second case, sigma y sigma z. So sigma y is we have seen just now 7550 h cross. Sigma z is equal to we have seen in part C 12 by 25 over h cross. So if you multiply both, you will get 84 divided by 125 h cross square. So which is equal to or greater than h cross over 2. Here yz, so naturally this will become sx. So sx, the expectation value of sx is 0. We have seen in section P. This is 0. Naturally this is 0. 0. Anything is greater than, here it is greater than 0. This is a trivial case. So naturally this also satisfies uncertainty principle. Now you come to the third one. Sigma Sx, Sz, sigma Sx. Sigma Sz, we have seen 12 divided by 25 h cross. This one. Then sigma Sx, that is h cross over 2, we have seen. If you multiply both, you will get 12 divided by 50, h into h cross square, which must be greater than or equal to h cross over 2, the modulus of the expectation value of Sy. So h cross by 2 I have written. Then Sy, in section P, we have seen the expectation value of Sy is equal to 12 divided by 25 h cross. So now h cross, you will get h cross squared, and 12, you have 12, 2 into 25, 50. Exactly same. So it must be exactly same or greater than this number. So this number is greater than or equal to the right hand side number. So this also satisfies the Pauli exclusion principle. Thank you very much for watching my video and supporting me continuously. Thank you very much.